Hey, welcome to another live coding. Um, Today we're going to mostly play around with different pre-processing options. And we're going to use a data set for magnetic tiles, which soon will be coming out as an instant model as well. So also a new series called Instant Model has been released on our channel. So go check it out if you haven't. It's, as the name sounds, very quick models with good use cases. So we're going to use the same data set where there's a bunch of magnetic tiles, for example on an assembly band, and we want to find which ones are anomalous. But since the instant model will show you how to build a basic model for it, we're going to skip the model iteration part on the model itself and jump to just using that model and testing different types of pre-processing on it, seeing if we can affect the results. So yeah, let's start with looking at the data set. It looks like this. It's we have these different folders. Each is one different class, as usual, for image classification, which will be here as we're doing anomaly detection. We have the different anomalies, as I mentioned, the blowholes, breaks, cracks, frays, uneven, and also free, which is the ones that have no anomalies. And if we take a look in these folders, it can look, this one has very few samples in it, but it looks something like this. And you may notice that there's two images with the same names. And that's because one is a JPEG and one is a PNG. And this data set can actually double for segmentation, which is the cool thing. So if we jump back into one of these again, you can see that these PNGs are masks. So what we're doing now is just going to classify the different magnetic tiles and the different anomalies inside them. But using this segmentation, you could also see where the anomaly is in the magnetic tile. So yeah, another thing to note with this data set, just quick before we jump into the model, is that this free category, or the category without any anomalies, is much larger than the other ones. And it essentially creates a very unbalanced data set if you were to use this just as it's downloaded. So what I did is I just took the first 150-ish samples from this one, and that balanced the data set out and made it a lot better to train on. And that's easy enough to do after you have everything sorted in the CSV. You just delete the rows you don't want, or you don't even add them when you're creating the CSV file. All right, so let's jump into the modeling part of it. So I'm going to start with just creating a baseline model, the same model that was used for the instant model video. And let's load this. It's using a standard mobile net and then 2 dense layers after. So something we've seen a fair bit in the live coding. But there's one little quirk to it, and that's that these images are grayscale instead of RGB, as they usually are. And if we try to connect a mobile net to a grayscale, it starts complaining. Input requires 3 channels, which means you need colored images, RGBs. So there are a few ways to go around this. The easiest one, in PerceptiLabs at least, is just toss in this convolution layer. And then you set feature maps to 3, stride to 1. And you now have RGBs, kind of. And then you can connect up the mobile net to it, and you can connect the mobile net to the rest of the model. And this one needs to change to softmax. And this will work great. Let's start training it. The benefit also with this dataset is fairly small, so you can do a lot of tests on it without taking too much time during the training. So this one we should get around 80% accuracy of the model, just without changing anything else. And we can do the normal things of looking at gradients and everything, but this model will train, at least it will, yeah. It won't flatten out the gradients or anything like that. Now you might be noticing that we're not really achieving the 80% accuracy, as I mentioned before. And I don't know if I said how this one works. This is one of the new additions to the statistics view, but it's essentially a confusion matrix, and how you read it is for class 0. We have predicted class 0 0 times, 1 0 times, etc., etc. For this one, for class 3, we predicted class 0 54 times, class 1 70 times, etc., etc. So if you're predicting the correct class on the correct label, which essentially this bottom one tells you, you know that your training is going well, your model is performing well. So if you're familiar with the confusion matrix, it's exactly the same thing, just flattened. And I'll show a better example of it. Anyway, as I was saying, you may be noticing that we're not really achieving those 80% I said that we were going to with this model. And that's because this model has one large issue. Using convolution as a converter to RGB works, but it's dependent on the initialization, which means that sometimes you will get really good results and sometimes you may get not as good results. So the first thing we're going to do is actually none of the new PerceptiLabs pre-processing. Instead, we're just going to replace this one. And we don't have any RGB converter in PerceptiLabs right now, but what we can do instead is just drag in a custom layer and do like this. So how the custom layer works briefly, you can custom write code in it, any Python code you want really, and it will execute it just like any Keras component, Keras layer. So what we're going to do here is take this input and just convert it over to RGB. And we can do that easily by TensorFlow image grayscale to RGB of the image, and then save that. Sorry, input, not image. And there we go. And how TensorFlow does this RGB, it just stacks this grayscale 3 times on top of each other. And now we can use this one to plug it straight into the mobile net instead. As we can see, all of this works, and we should be able to run it. And hopefully we will get a bit better results now, because we're no longer dependent on the conv layer initializing properly. Okay, there we go. And we're already at 80% validation. And we can see this one looking a lot better now. And now it's easier to read. As you can see here, 0, we're predicting zeros for class 1. We're predicting mostly class 1, etc., etc. And you can see a little bit what different classes it mispredicts. So class 2 seems to mix up with class 3 a bit more than the others. And that way you can really see if two classes gets mixed together more than any other, or if there's a big class imbalance between your different classes that you're training on. Okay, so we did that change, and we're already up to almost 90% accuracy, 125 we had before. Now, if we had ran the conv layer one or a couple more times, I'm sure we have gotten this result as well. This is just an easier and quicker way to achieve that. Okay, so now we have a decent baseline which we know will perform okay each time we run it. There's no, we can run it again and it's probably gonna shave over 80%. There's not gonna be a huge variance to it. So let's go ahead and create a new model. And let's cleaning this one up. And this time we'll add some pre-processing to it. And we have a few pre-processing. We have normalize, which I don't think we're going to need to do. Normalize is already happening automatically in the mobile net, so that one should be fine. But we can look at random flip, which is an augmentation technique. It's going to randomly flip every random image. And either both vertically and horizontally. You can choose here. But essentially just randomly select images which it will flip. And this obviously makes the model more robust to flipped images, but it also artificially increases your dataset. So we would have essentially more samples we can train on. So if we train for more epochs, or we could train for more epochs without starting to overfit, which is the beauty of this. We then have random rotation, which works very similarly. It's just rotating the image. And random cropping, which crops out a small part of the image and uses that as input. Random cropping works best with segmentation of huge images, where you crop a small part of both the input image and the mask. And that way you can segment, you can do partial segmentations or train on partial segmentations without having to train on the huge 5K images or whatever you may have if you're doing some really detailed medical or if you're looking at geo images or things like that. So let's start with the random flip and see how that one works. We just delete this one. And run it, and this time we can run it for more epochs, so we can double the amount and see how that works. And again, the reason we can comfortably run on more epochs is we'll have artificially increased our dataset. We're also having an update coming in fairly soon where you don't need to create a new model every time you want to change the pre-processing settings. Instead, you'll be able to open the data wizard inside of the workspace. So you can very easily, rather than go, as I did, go out, create a new model, you'll very easily just be able to change the pre-processing settings inside of your existing model, which makes it a little bit easier. Okay, so far it's looking very similar to how it did before. Let's see if it just keeps oscillating around that, or if it drops down. Okay, so the validation went up a bit and the training went down. Another interesting thing to look at is the loss function. So from this larger loss function, which you see in the target, it's not very easy to tell how much what difference it actually is. If you go in here and look at this one, and I'll see if I can get a better example if we start overfitting. But it'll be much easier to see if the validation has a higher base value than the training training loss has, which you sometimes can't see that well from this one. I mean, you can always zoom in, but it's hard to get a grasp from just one point. What we can do here is we can guess that it wasn't finished training yet, and we can keep training it for a little bit longer. It would be nice to also activate the other one, but let's go back and run it. Let's try running it for a bit more epochs and see. And what I'm looking for here is really just to see when we start overfitting the model. Question if we can see the augmented images for sanity check. You can, or rather, you can catch them as they show up here. However, that's you do need a little bit of luck to see them. For some, it's very easy to see. For some, these ones it's not as easy to see. It's a good question though. Maybe it would be good to have a view where you can inspect the data, and we actually have some ideas around that. Something called a data hub, where you would be able to inspect your data a little bit closer and maybe even browse through all the samples. So if you do enable some pre-processing, some augmentation, you could see some samples of how that would look like. Okay, let's see how this one's looking so far. No overfitting yet. I'm going to look mostly here to see if we can detect some overfitting to it. But so far it's training really good. It's oscillating a little bit, but it's in general going down, it looks like. Also take a look quick at these gradients as well to see if they're changing much. They seem to be increasing, which means that the model is updating more and more in this component each epoch. Alright, we still got decent accuracy. It looked like we started overfitting somewhere around here a little bit. And you can see here the validation. Usually it's even more noticeable, but you can see it start going up a little bit compared to some of the training values. And we can also notice a dip here in the training accuracy and validation accuracy. Okay, so let's try the other pre-processing. Actually, think I can copy this one over to the next model, so I don't need to do that one all over again. Alright, so let's enable random rotation this time. And we can use reflect. All of these are exactly the same options as you would see in Keras if you use the Keras pre-processing. So you will have a clear documentation on how they work. Let's throw this in. Custom in. Unfortunately, can't copy paste custom layers quite yet. There will be there's an issue with the name if you try to do that, so you might get a crash. But the rest of the components should work fine. There we go. And then we run it. We can just run it for 10. And this one should be more noticeable in the images. This one should rotate every image by a random amount. Well, I think I put the factor to 0, so we might have to quickly redo that one. Yeah, we can stop this one and redo it. We're not seeing it rotating. So let's do the exact same thing. But this time we change the factor. And the factor is between minus p and p. Minus pi and pi for the entire circle. So just put 0.5 and see how that one works. Let's get the custom layer in. There we go. Now we should see a difference. So one feature we should have is probably show the original compared to the augmented. That would be pretty cool. Let's see how this one performs training wise. Well, so far it seems like it's not liking the rotating. The flipping was much better. Which might make sense. It might start mixing up different classes here, depending on what angle different anomalies are. On the other hand, you would probably also argue that you would want your anomaly detector for different types of anomalies to be invariant to what angle you look at them. And that's another part of the pre-processing. Sure, it augments your dataset and you get increased dataset, which may improve your training accuracy. But accuracy is not always everything. The main benefit is that you start getting invariance to these kind of things. So if you, for example, randomly blur an image, you start getting invariance to that. If you randomly flip or crop an image or randomly obscure an image, you start getting invariance to that, and getting a good model for those cases might be more valuable than just getting the larger data set and getting a high accuracy on the base data set. And that's the final piece of advice for today. To summarize, we quickly took a look at the what is it called now again? The magnetic data set and how it works in detecting anomalies in it, and then tried out a bunch of different or a few different pre-processing options. And most noticeable was the RGB or grayscale to RGB, but then we also saw the random flipping, which didn't seem to have much of an effect. I believe we could probably train it a bit longer without getting overfitting than we could the original one. The original one started getting overfitting pretty quickly after just 5 epochs. But the random rotation one, on the other hand, had worse performance. But arguably that's because it's more difficult to learn that invariance. So thank you very much everyone for joining me for the live coding. I hope you all have a great Thursday and take care. Until next time.